Question 924. The number of a squirrel in a national park is modeled by the function s that satisfies the logistic differential equation ds over dt is this expression, where t is the time in years and s of 0 is equal to 800. Find the value of limit as the t approaches infinity s of t. Okay, in general, if y represents the population, then the logistic model can be represented by the following differential equation. dy over dt is equal to some constant k times y and carrying capacity L minus y. Okay, and the solution curve y looks like, here we have a carrying capacity, which is maximum population. Here is initial population, and it increases with the concave up like this, and then there's a point of inflection here, and it increases with the concave down like this. This solution curve, the population curve, right? This curve is called the logistic curve, and it approaches to the carrying capacity L as t approaches infinity. Okay, and as you see it, curve always increases, right? So dy over dt is always positive for all t, and we have a point of inflection of the curve y when the population is exactly half of carrying capacity, which is L over 2. Okay, so up to this point right here, our second derivative y double prime t is positive here, and y double prime t here would be negative. All right, so we know that at this point right here, our y prime is maximum, right? One more thing that we have to know is that our slope, which is dy over dt, approaches 0 as t approaches infinity, right? If we look at this logistic curve right here, it increases, right? But as t approaches infinity, our slope, look at our slope. Our slope is going to approach 0, right? Because the population is approaching L, which means there's no increase in population anymore as t approaches infinity, right? So as t approaches infinity, remember that our slope approaches 0. Okay, so back to this problem right here. As t approaches infinity, what does s of t approach to? Here, the population is s, right? So this is s of t, and our carrying capacity L is 9,600, right? So this is 9,600. And initial population is 800. So here is 800. So as t approaches infinity, this population approaches to its carrying capacity L, right? Which is equal to 9,600. That's our answer, right? Question 925. Find the maximum rate of change in squirrels per year of the number of squirrels in the park. Okay, here we have a population of a squirrel, and our carrying capacity is 9,600. So that's maximum number of squirrels. Okay, the question is to find the maximum rate of change. Rate, right? ds over dt. Well, the population of squirrel looks like it increases with the concave up and concave down, right? This is our point of inflection, right? And that happens when the population is exactly half of this carrying capacity. So 9,600 over 2, right? And this is where our first derivative, ds over dt, is maximum, right? So our maximum rate of change, maximum value of ds over dt is equal to 1 over 25,000 times when s is equal to, well, 9,600 divided by 2, that's 4,800, right? 4,800 times 9,600 minus 4,800. So that's going to be equal to, here eliminate 2 zeros from numerator and denominator. So that's going to be 48 over 250 times 9,600 minus 4,800. That's 4,800, right? So if we use our calculator, that's going to be equal to 921.6. And our unit is in squirrels per year, right? Squirrels per year. That's our maximum rate. Question 926. Find the second derivative of s with respect to time t in terms of s. Well, here we have first the derivative of s with respect to time t, right? So our second derivative is equal to, this is the constant, right? So leave this one alone, 1 over 25,000. And here we have s times 9,600 minus s, right? So we're going to have to apply the product rule, right? So derivative of s, that's ds over dt. And we have 9,600 minus s plus s times derivative of this 9,600 minus s. Well, that's just a negative ds over dt, right? So that's going to be equal to, we have 1 over 25,000. Here we have ds over dt and ds over dt here, right? So we're going to factor out ds over dt. Then we have 9,600 minus s minus, well, actually plus negative s, right? So minus s minus 2s. Does that make sense? And our ds over dt is right here, right? Since we have to write our second derivative in terms of s, we're going to have to rewrite this expression times 1 over 25,000 s 9,600 minus s times 9,600 minus 2s, right? So if we simplify this, we can just write here 1 over 25,000 times 1 over 25,000. That's 1 over 25,000 squared as 9,600 minus s 9,600 minus 2s, right? Question 929. The number of people in the mall at time t is modeled by the function p, the solution to a logistic differential equation. The maximum number of people allowed in the mall is 6,000. At 12 p.m., the number of people on the mall is 1,600 and is increasing at a rate of 800 people per hour. Which of the following could be the logistic differential equation? Okay, the logistic differential equation with the population p is given by dp dt is equal to some constant k times p carrying capacity L minus p, right? Here, the maximum number of people allowed in the mall is 6,000, right? So our carrying capacity is 6,000, and the number of people in the mall looks like it increases like that, right? At 12 p.m., the number of people on the mall is 1,600, and it is increasing at a rate of 800 people per hour, right? So let's say this is 12 p.m. At this point right here, the number of people in the mall is 1600, and at this point right here, our rate, slope of this tangent line, which is dp dt, is equal to 800 people per hour. So that's 800, right? Now let's substitute these values in this logistic differential equation. So when P is 1600, our rate is 800, right? And our carrying capacity is 6,000. So 6,000 here. So we have 800 is equal to some constant k times 1600, 6,000 minus 1600. Right, now let's find the value of k. Here we have 800, 1600. So cancel this one out and this becomes 2, right? 6,000 minus 1600, that's 4,800, right? So 1 is equal to k times 2, 4,800. I'm sorry, that's a 4,400. 4,400, right? So k is going to be equal to 1 over 2 times 44, that's 8,800, 8,800, right? So our differential equation dp over dt is equal to k, 1 over 8,800, P times carrying capacity 6,000 minus P. So the answer must be A. Okay. Question 932. The number of wild deer in a mountain is modeled by the function d that satisfies this logistic differential equation, where t is the time in month and d of 0 is 250. Which of the following statement is not true? Okay, our logistic differential equation is dd over dt is equal to, well, in this problem, the population of wild deer is d, right? That's going to be equal to some constant k times d and carrying capacity L minus d, right? Here we have a dd over dt is equal to 0, let me write right over here, 0.05 d 2 minus d over 1200, right? What I'm going to do now is I'm going to factor 1 over 1200 from this term to make all of this expression to this expression right here. Okay, since we have d here, I'm going to factor out 1 over 1200. Okay, so that's going to be equal to 0.05 d, and we have 1 over 1200. Then this is going to be 2 times 1200, 2400, right? Because the 2400 divided by 1200 gives us 2, right? So minus d. Okay, so that's going to be equal to 0.05 over 1200. That's our k. D carrying capacity is 2400 minus d. So this carrying capacity is 2400, right? Now let's look at our answer choices. A, dd over dt is positive for all these from 250 to 2400. Our initial population was 250, right? So this is 250 and our carrying capacity is 2400. So from here to here, our logistic curve, the population curve always increase, right? It always increases. So dd over dt is always positive. That's true, right? That's true. B, our second derivative is positive for all these from 250 to 1200. Well, we have a point of inflection when our population d is half of carrying capacity, which is 1200, right? So from here to here, our curve is concave up, which means second derivative is positive in this interval, right? So that's true. C, well, there's a typo here. This is 1200 and this is 2400. And it says our second derivative is positive for all these from 1200 to 2400. Well, our population curve is concave down in this interval, right? So this is not true. This is false. So not true. The answer is C. Okay?